Okay, here we're going to have a recording that will address several questions that students have asked about homework problems in MyMathLab from sections 12.4 and 12.5. And we will begin with section 12.4, problem number 12. In problem number 12, we're asked to find the derivative of an exponential function, y equals e raised to the power of a product, which is x times the square root of the quantity 9x minus 17. The derivative of e to the x is the easiest one to take because the derivative of e raised to any power is simply e raised to that power. Our problem comes from the fact that the power in this case happens itself to be a function. And chain rule tells us that we will first multiply out the derivative of the function, that is the power, and then multiply it times the derivative of e to the power. So we're going to take this step by step. The first thing that we'll do is we'll find the derivative of the power. And the derivative of the power, since the power is x times, and we'll write the square root of 9x minus 17 as 9x minus 17 to the 1/2 power. So when we take the derivative, this is a product rule. And taking the product rule, we take the first factor, which is x, times the derivative of the second factor, which is 1/2, times 9x minus 17, and then 1/2 minus 1 is a negative 1/2 power. And to that we will add the second function, which is the 9x minus 17 to the 1/2 power, and multiply it times the derivative of the first factor, which is 1. So at this point, it would probably be a little simpler to clean this up just a bit since we have to use it in a subsequent step. So the first thing that I'm going to do is I'm going to multiply the x times the 1/2 and get x over 2. And then, since this power is negative, I'm going to change it back to a radical and put it back in the denominator. So that's going to be over the square root, which is what the 1/2 power is. Putting it in the denominator takes care of the fact that it's negative 1/2 power. The radicand stays the same, 9x minus 17, and I'm remembering here that I forgot a step. I should have also taken the derivative of 9x minus 17, so its derivative here would have been times 9. So that means 9 times x in the numerator is going to be 9x plus 1 times, and again I'm going to change the 1/2 power down back to a square root, the square root of 9x minus 17. So then our next job is going to be to take the derivative of e to the power. So y prime then will be e to the same power. The power does not change. And we're going to multiply that, according to the chain rule, by the derivative of the power, which was 9 times x over 2 times the square root of 9x minus 17 plus the square root of 9x minus 17. Now we could multiply each of these two terms by e raised to that power, but that isn't actually necessary. If the book were to give you a multiple choice question where they actually have done that, then an alternate form of the derivative would be 9x e to the x times the square root of 9x minus 17 all over the square root of 9x minus 17, which was multiplied by 2, plus e to the x times the square root of 9x minus 17 times, or you actually could leave out the multiplication symbol, you really don't need it, and just put in the radical instead, the square root of 9x minus 17. And that would be your other version of y prime, the derivative. Our second problem, which is problem number 13 in 12.4, says that the sales in thousands of a new type of product are given by S of t is equal to 70 minus 90 e raised to the negative 0.1 t, where t represents the time in years. Find the rate of change of sales at the time when t is equal to 2 and round to the nearest tenth. Well, the rate of change, anytime we're asked to find a rate of change, we're asked to find the derivative. So the first step of this is going to be to find the derivative, which is s of t. And that's going to be prime. Or that could be written ds dt. Both mean the same thing. And the first term in our sales function is a constant, 70, and of course the derivative of a constant is 0. The derivative of 90e raised to the negative 0.1 t power would be keeping the 90, because it's a coefficient and it's a hitchhiker. It's e raised to the same power, which is negative 0.1 t, and then we also again will have to take the derivative of that, and the derivative of that power is going to be the derivative of negative 0.1 t, which will be simply negative 0.1. So s prime of t, we'll leave out the 0. Subtracting and times negative is going to make our result positive, and 90 times 0.1 is 9, times e raised to the negative 0.1 t power. So this is our rate of change. And that's our rate of change for sales. And we're asked to find the rate of change for sales when t equals 2. So s prime of 2, which is 2 years after sales began, is equal to 9 e to the 0.1 times 2 power. And the units on our sales is going to be 1,000 products or 1,000 units per year. You have to remember that these are always in context. So at this point, I'm going to pause, and at this point, I'm going to use the calculator to evaluate (9e) to the negative 0.2 and round that to the nearest tenth. So that's going to be, what I have on my calculator is 7.368, which means that it is going to be 7.37 thousand units per year. So when you answer the question, your answer is going to probably ask you to actually change that into 1,000 units. So 7.37 times 1,000 is saying that we have 7,370 units per year. At 2 years. Or you could alternately say 2 years after sales began. This is problem number 14 in section 12.4. Says the demand function for a certain book is given by the function x equals d of p, which is 53 times e raised to the power negative 3 1,000ths times p, and it wants us to find the marginal demand, d prime of p. So all we're actually needing to do here is take the derivative. But again, the power on our e is itself a function, so we'll have to be sure and take the derivative of it as well. So, to begin, d prime of p the 53 is going to ride along as before. E is going to still be raised to that same power, negative 0.003 times p. But again, we're going to multiply by the derivative of the power itself. And the derivative of the power itself is simply negative 0.003. So using the calculator, I'm going to multiply negative 0.003 times the 53 and get negative 0.159. So that's the product of the negative 0.003 and the 53. So then the rest of the function is simply the e raised to the power. And that is d prime of p. And that is the marginal demand. And since we don't know anything about the units on this, then this would be the complete answer. Okay, here we have a problem in still section 12.12.4, problem number 15. And this problem is going to depend upon our knowing what a logistic function for growth looks like. So let me pause for a moment to actually explain that part to you. A logistic function is a function that looks kind of like this. And since this growth function, we're going to call it g for growth, so it's g of t. It's a rational expression. And the numerator of the rational expression is m times g sub 0. And we'll talk about what those constants are in a second. And the denominator is g sub 0 plus the difference between m and g sub 0 times e, and the power on e is negative kmt. And in order to fill in this function, we need to figure out what some of these things are. So I'm going to start out by helping you identify g sub 0. G sub 0 is the initial number that is present at time t equals 0. So g sub 0 is given in the problem. It says when t equals 0, the number of users was about 4 million. And g of t is in million users. In year t. So that means that g sub 0 is 4. And then we need to also think about what m is. M is the maximum possible size. And the problem also tells us what that value is. It says the number is expected to level out around 210 million. So m is 210. And then the last thing that I need to put it in here too, sorry. And then the last thing that we need is the constant k, and it tells us the value of k. It says that k is 0.0016. Now, before I get started simplifying quite everything, I'm going to try to multiply a few things out. So 210 times 4 is 840. And as we've said, G sub 0 is 4. And 210 minus 4 is 206. And 210 times 0.0016 is negative 0.336. So we have our logistic function. However, we can factor out in the numerator and the denominator a 2 because both 4 and 206 are even. We'll divide both of those by 2. And the denominator will become 2 times 2 plus 206e to the negative 0.336t. And we'll also factor out a 2 from the numerator so that the 840 becomes 2 times 420. And take out both of those 2's. And this is simply to make the function a little more compact. You actually could use it the way that it was to begin with. But at this point, we will actually be able to pick it out of the multiple choice that we're given in the problem. So we now have our function for g of t. G of t is equal to 420 over 2, and I just realized I made an error. That's no longer 206, it's 103. 2 plus 103e to the negative 0.336t million internet users. T years since 1990. And including the units actually makes it much, much, much easier for you to be able to employ that function and use it in parts B, C, and D. So at this point, we're given several values for t. The first one is 1994. In 1994, that is 4 years after 1990. So we are going to find g of 4, which is 420 divided by 2 plus 103e raised to the negative 0.336 6 times 4. And since we're going to have to do several of these, I'm actually going to plug that into the calculator and use the y1 function. So when I do that, one thing to remember is that when you're plugging this into y1, that you're going to, you don't have to put parentheses around the numerator because it is a single number. So it'll just be 420. It's going to be 420 divided by, use parentheses around your denominator, 2 plus 103e raised to the power, and it's automatically going to open parentheses for that. Be sure and use a negative, not a subtraction sign, 0.336x, and close your parentheses. So that's what you're going to put in y1. So I'm going to pause for a second and enter that into my calculator. Okay, I have the function in my calculator. You can either use the vars menu and do y-vars, y1 of each of these numbers, or you can use the table in the ask mode and ask it for the values that I'm going to outline here for t. So the first one we ask for is t of 4, and t of 4 gives us 14.552. And that's going to be 14.552 million, which is times 10 to the 6th, users in 1994. I'm not writing that answer out, but you should be prepared to do that on a test. In 2001, the value would be 11 years. So that would be t is equal to, and so that's 92.171 million users in 2001. And then in 2010, the value of t is equal to 20. So we have g of 20, and g of 20 turns out to be 197.71. And since that's in millions, I'll go ahead and translate that one. 197.71, we're going to move the decimal 6 places. Which gives us 197,710,000 internet users in 2010. Now, in order to answer the last question, which says, what happens to the rate of growth over time? What we can do on that table, which is why I chose to use the table, is to simply add in more and more years. And since we've put in 20, I'll put 25, 30, 35, 40, 45, and 50. And by putting in those larger and larger numbers, this is what I see happen. At 20, of course, it was 197.71. At 25, it is 207.6. At 30, it is 209.55. At 35, it is 209.92. At 40, it is 209.98. At 45, it is 210. I'm sorry, at 45, not 48. And at 50, it's still at 210. So what happens over time? Well, what we see is that over time, the number of internet users will level out at 210 million users. And that answers question E. Here we have question number 4 in section 12.5, and it asks us to find the derivative of the function y equals ln x plus 1. And we have a little bit of a typo here, so I'm going to just X that out for right now. So we need to figure out how to take the derivative of the natural logarithm, and the easiest way to do that is to consider the formulas. And again, this is going to employ chain rule. Okay, here we have section 12.5, problem number 4, and we want to find the derivative of y equals the natural logarithm of the function square root of x plus 1. And here again, we're going to have to use both the derivative for finding the derivative of a natural logarithm, which if f of x is ln x, then the derivative f prime of x is simply 1 over x. However, since our x is an actual function, chain rule says that our f prime, because our x is an f of x, our f prime of x is going to be 1 over f of x times the derivative of f of x, which we'll write as d over dx of f of x. So I guess we would be better off calling this, instead of f of x, let's call it g of x so that we don't get confused. So that's the pattern that we're going to follow. And in this case, f of x is x plus 1 to the 1/2 power. So in finding the logarithm, we're going to need not just the derivative of g of x, but the derivative of f of x. So f prime of x is going to be 1/2 x plus 1 to the negative 1/2 power. So now we'll begin doing the actual logarithm of our function. So our function is y equals ln of x plus 1 to the 1/2 power. And thus y prime will be 1 over x plus 1 to the 1/2 power times the derivative of x to the 1/2 power, which is 1/2. And in this case, because my 1/2 power is negative, I'm going to go and put it in the denominator also. And that means then that y prime is equal to 1 times 1 is 1 over 2 times x plus 1 to the 1/2 power. But because there's two of those, they're x to the 1/2 times x to the 1/2, that's x to the 1/2 squared. Here's where your rules for exponents are going to come back in. And since 1/2 times 2 is equal to 1, then our derivative is 1 over 2 times the quantity x plus 1. And if you want to simplify that further, you can. One over 2x plus 2. So this version right here would have been perfectly fine, although not nearly as easy to type as this one. So here we have 12.5, number 13. And there's a little bit of stray information here, so we will just simply kind of ignore that stray piece of information. That actually goes on the next slide. says to find the derivative, and here again we're going to use chain rule. So we're going to find the derivative of the function f of x, and f of x is the natural logarithm of a function. So the inside function for our chain rule here is going to be x e raised to the square root of x plus 5, and we will need to find its derivative. So we will call this, since I call it the inside function, we need to find the derivative of the inside function, which I'll call I prime. And the first part of that is a product. So the first thing we're going to have to do is take x times the derivative of e to the square root of x. And the derivative of e to the square root of x is e to the square root of x times the derivative of the square root of x plus e to the square root of x times the derivative of x. Now, the derivative of the square root of x is the derivative of x to the 1/2. And that's going to be 1/2 x to the negative 1/2, or 1/2 square root of x. And of course, the derivative of x is just 1. So then we have that the derivative of the inside function, remembering that that's what's in the parentheses, is x e to the square root of x times 1/2 square roots of x plus e to the square root of x, or alternatively, if we multiply this through, we have x e to the square root of x over 2 square root of x plus e to the square root of x. And this first term here was just simply multiplying this times 1 over the square root of x. So here's a derivative of the inside. Now, the derivative of the outside is the derivative of the natural log function. So when we take f prime, the derivative of the natural log is simply 1 over whatever you've got, which is x times e to the square root of x plus 5. And if you wonder what happened to the 5 in taking that derivative, you should remember that that derivative was a 0. And we're going to multiply that times I prime. So f prime of x is equal to 1 over x e to the square root of x plus 5 times the quantity x e to the square root of x over 2 square root of x plus e square root of x. And there's probably some idiot that would want to simplify that, but I would leave it just exactly like it is. Just be very careful that you type it in exactly that way. Section 12.5, number 14 says to assume the total revenue from the sale of X items is given by R of X is equal to 31 times the natural log of X, times the natural log of the quantity, 6X plus 1. And the total cost to produce those X items is C of X equals X over 4. Find the approximate number of items that should be manufactured so that the profit, which is R of X minus C of X, is maximized. First, we need to find R of X minus C of X. So R of X is 31 ln 6x plus 1 minus 1/4 x, or you can leave it as x over 4. I'm going to change it to 1/4 x. And if we want to find where the profit is maximized, that means that we're going to want to find out where profit function, which we're going to call P prime of x, is equal to 0. And this actually is our profit function, P of x. So we need the derivative of that profit function. P prime of x is equal to 31 times 1 over 6x plus 1 times the derivative of 6x plus 1, which is 6, minus the derivative of 1/4 x is simply 1/4. The x disappears. So P prime of x, to clean it up a little bit, we have 31 times 1 times 6. 6 times 31 is 183 over 6x plus 1 minus 1/4. And if that is equal to 0, that means that 183 over 6x plus 1 must be equal to 1 over 4. So if we cross multiply, four times 183 is equal to 6x plus 1 times 1 is simply 6x plus 1. Then we will have 6x is equal to whatever 4 times 183 is. It's 732 minus 1, which is 731. And 731 divided by the 6 in front of the x is 121.8333. So we need to answer the question. Profit is maximized at 122 items for, and they didn't ask us what this was, but since the profit is 31 times the natural log of 6 times 122 plus 1 minus the cost, which is 122 divided by 4, and that is the quantity 122 divided by 4. So be sure and put parentheses around that. Maximum profit is assuming that this is in dollars, $174.01. And since this is going to be an approximation, we'll just leave it at that. Now, just to verify that you actually should round, I'm also going to go and plug in 121 rather than 122, and I see that the profit is $174 also. So it doesn't hurt to make the extra item. Be sure and round the way that MyMathLab tells you to. Okay, here we have a section 12.5 problem, number 15. Says, suppose that the demand function for X units of a certain item is P equals 110 plus the fraction 210 ln of the quantity X plus 5, all divided by X. And P is the price per unit in dollars. So if you're looking for a revenue function, which you'll obviously have to find to get marginal revenue, you need to remember that revenue is equal to the cost per item and that's times the number of items. And that what we're going to want to find is R prime, and that's dr dx. So the first thing we're going to need to do here is actually write the revenue function. Now the revenue, since it's price per item, and P is the price per unit, so that's price per item, So we will take this to be the price per item. So that's 110 plus 210 ln of x plus 5 divided by x, and the number of items is x because that's the number of units. So then this means that our revenue function is 110x, because you're multiplying the x times the 110, plus when you multiply x times the second term, your x's are actually going to cancel out, leaving you with plus 210 ln of x plus 5. And I goofed up and put two sets of plus signs, so we really actually only need one. So here's your revenue function. And we need r prime of x, or dr dx. And we're going to do this term by term, so r prime of x is going to be 110, the x will drop out on the first term, plus 210 times the derivative of ln x is 1 over x plus 5 times the derivative of x plus 5, which is 1. So that means that r prime is equal to 110 plus 210 over the quantity x plus 5 and that is, in dollars was the price per unit times units is dollars per unit of revenue. And actually we don't need to complete that last part because it's the dollars per unit for however many units are sold. So this is the change of rate of revenue, that when you sell X dollars, your revenue is changing by R prime of X. Okay, here we have section 12.5, problem number 16. And problem number 16 gives us the cost function for Q units, Q standing for quantity of units, of a certain item as C of Q is equal to 90 times the number of units plus 104. And the revenue for that same item is R of Q for Q units, is 90 times Q, the number of units, plus 46 times the number of units divided by the natural logarithm of the number of units. And the first thing that we're supposed to find is to find the marginal cost. And the marginal cost is C prime of Q. And C prime of Q is actually a relatively easy problem, relatively easy function to take the derivative of, because the derivative of 90Q is 90 and the derivative of 104 is 0. So C prime of Q is 90, and that should make sense because the marginal cost here is the slope of that function, which is 90. So it doesn't matter what the value of Q is, it's always going to be increasing by $90 per unit. Find the profit function. Now, the profit function isn't given to us, but we know the profit from selling Q units is going to be equal to the cost of those units. Sorry, I'm writing this backwards. The cost of those units subtracted from the revenue for selling those units. And of course, hoping that profit is positive and that the revenue is actually more than the cost. So in order to find the profit function, part B, P of Q, first we take R of Q, which is 90 Q plus 46 Q divided by the natural log of Q, minus C of Q, which is minus 90 Q plus 104. And now simplifying this profit function, we have 90 Q plus 46Q over natural log of Q minus 90Q minus 104. And since 90Q and minus 90Q will cancel each other out, our profit function, P of Q, is 46Q divided by ln of Q minus 104. And that is profit in dollars, so that's dollars profit for the sale of Q units. And our last problem says to find the profit from one more unit sold when 8 units are sold. Well, in order to do that, the very first thing we're going to have to do is we're going to have to find P prime of Q and then substitute in the number 8. So we're going to start out by finding P prime of Q, and I need a little more space. So I'm going to eliminate the work here that we used to find P of Q so we can find its derivative. So the derivative, P prime of Q, well, let's see. ln Q and 46Q are forming a quotient, so it looks like we'll have to use quotient rule. That means that we'll take the denominator, ln Q, times the derivative of the numerator, which is 46, minus the numerator, which is 46Q, times the derivative of ln Q, which is 1 over Q, and then minus, let's complete this part first. So we're going to divide that by ln of Q, and that value is going to be squared. And then the 104 is going to have a derivative of 0. So this is actually our complete marginal profit function. And our marginal profit is in dollars per item. So now to proceed with answering the question, find the profit from one more unit when you sold 8 units. That would be P prime of 8, which is equal to the natural log of 8 times 46 minus 46 times 8 times 1 over 8, all divided by the natural log of 8 squared. So now we need to do some arithmetic. So, getting started, we know that 8 times 1/8 is 1. We can just kind of forget about that. When we multiply the natural log of 8 times 46 and then subtract 46, we get approximately 49.65. We're going to divide that by the natural log of 8 squared. And the final answer that we get as a result of dividing the numerator by the natural log of 8 squared, which is 4.32 approximately. And I'm rounding these off so they're not exact. Our final answer is that P prime of 8 Here we have section 12.5, number 17. Number 17 says the total revenue received from the sale of X items is given by R of X, which is 50 times the natural log of the quantity 4X plus 1, and the total cost to produce those items is C of X is equal to X divided by 4, and we are to find the marginal revenue, the profit function, the marginal profit when X is 200, and explain what that means. So the marginal revenue function is simply the derivative of the revenue. And the derivative of 50 ln the quantity 4x plus 1 is equal to 50. The coefficient just rides along. The derivative of ln is 1 over the quantity 4x plus 1. And then that's times the derivative of 4x plus 1, which is just 4. And so that we multiply our fractions properly, I'm going to put everything over a 1. So r prime of x is equal to 50 times 4. Let's just go ahead and multiply that out. That's 200. Divided by 4x plus 1. Now, the profit function, P of x, we get by subtracting the cost from the revenue. So the profit is given by the function 50 ln, quantity 4x plus 1 minus, and rather than write that as x over 4, I'm going to call that 1/4 x to remind you that that's really a coefficient of 1/4. And then they want to know, find the marginal profit when x is 200. Well, first we need to find the derivative of the profit function. And since we already have the derivative of the revenue part of it, we're going to use the fact that that's 200 over 4x plus 1 minus the derivative of 1/4 x is 1/4. And in order to make our math a little easier, we will get a common denominator by saying 200 times the 4 minus 1 times the 4x plus 1 all over the common denominator of 4 times 4x plus 1. Now we could simplify that further, but the only choice I'm going to make to simplify it further is to change this to 800. And now to find p prime of 8. P prime of, I'm sorry, not 8, 200. My brain's still on the last problem, guys. We're going to have 800 minus 4 times 200 plus 1 divided by 4 times 200 plus 1. So 4 times 200 is 800. $800 plus 1 is 801, and 4 times 801 in the denominator is 3204. And 800 minus 800 is going to disappear, so we're only going to have 1 left. And I made an error as I brought this down, because when I multiply 1 times 4x plus 1, and remember that I'm subtracting, I do get minus 4x, and I also get minus 1. When I distribute my negative sign, that 1 becomes negative. So we need negative 1 over 3204. And that is negative 0.0000312. It actually comes out in scientific notation. So it says, interpret that. Interpret the results. Well, the result says that since we're talking about marginal profit at x equals 200, at 200 items, profit is, and because we are negative, it is decreasing $0.00312 per additional item. Now, that is not to say that we are not making profit. It's saying that our rate of change in profit is decreasing. So in other words, we're making less per item. Here we have section 12.5, problem number 18. Problem number 18 says the equation A of t is equal to 8,000 e raised to the 0.065t gives the balance after t years of an initial investment of $8,000, which I hope obviously is your $8,000, is obvious to you, which pays 6.5% compounded continuously. 6.5% is 0.065. And it says find a formula for the derivative of A. Well, the derivative of A, which is going to be A prime, is equal to the 8,000 just rides along times e to the 0.065 t, and then we need to multiply this whole thing by the derivative of 0.065 t. So we're going to multiply that whole equation, and I'm going to put it in front just to make it easier. So let's actually simplify that. Let's say 8,000 times 0.065 is 520. So A prime of t is equal to 520 times e to the 0.065 t. Then it says find and interpret A prime of 9. So that's 520 e raised to the power 0.065 times 9. Pause for. So to do the arithmetic, we've entered this all into the calculator, and we have come up that A prime of 9 is equal to $933.40. And what this means is that at 9 years of continuous compounding, at this rate, the balance is increasing. by $933.40 per year. Part C says compare the approximation of 933 to the actual change and report your answer to 2 decimal places. The actual change is the amount of interest from year 8 into year 9. So what we would do to answer this part of the question is we would need to find A of 9 minus A of 8. And I'll do that on the calculator and give you the values. So A of 9 is actually the amount $14,359 and 93 cents. And the balance at the end of year 8 is $400. Let me start again. $14,359.93 minus $13,456.20, well, 22 cents actually, which gives you an actual difference of $903.71. But remember, the difference between the two is that the actual change is the balance at the end of year 8 subtracted from the balance at the end of year 9, which is basically the slope of a secant line. Whereas our derivative is the amount of change approximately at the end of the 9th year going into the beginning of the 20th year. And that's why there's a little bit of difference in the two. Okay, here we have the last problem, which is from section 12.5, problem number 19. And it says that you plan to invest in an account that pays 4% compounded continuously. If the investment period is for 6 years, then A of P is P, the initial amount invested, times E to the 0.04t, and if the investment period is 6 years, then that is 0.04 times 6. So A of P for this particular setup is P times E raised to the 0.024 power. And that will give the total balance of P dollars at the end of 6 years. We need to first find a formula for A of P, the derivative of A of P, which is A prime of P. And A prime of P is the derivative of this function, keeping in mind that P is the variable that we're taking the derivative of A with respect to, and also take into account that E to the 0.024 is a constant. So basically this is E raised to the 0.24 times P, and when we take the derivative, all we're going to have left is the constant. This is similar to finding the derivative f prime of x if what you actually have is f of x is equal to 2x. And the derivative of that would simply be 2, because the variable is x, or in our case, p, and e to the 0.024 is serving in the same way that 2 does, in that 2 is simply a constant. And in our case, our constant is e to the 0.24 power. So that's your formula for a prime of p. If you plug in to that formula a prime of 2000, notice that actually for any principal, it doesn't matter what the principal is, for any principal, the rate of change is going to be e raised to the 0.024 power, as long as your original interest rate is 4% and the time period is for 6 years. So that's going to simply give you, when you evaluate e raised to the power 0.24 on your calculator, that gives you, rounded to the nearest dollar, or nearest cent actually, 1.27. And that 1.27, since this is a rate of change, is the dollars increased in the total amount per dollar increase in the initial value. In other words, when the initial value goes from 2000 to 2001, then you're going to get $1.27 increase in the initial value and $1.27 increase in the future value for every dollar that you increase the initial value. And that's because your interest is continuously compounding. The next formula the next question says to compare the approximation to the actual value. So since we're talking about the approximation, what we would want to do is we would want to find not a prime, but a of 2000 and subtract it from a of 2001. Not the derivative now, the actual initial function. So what you're going to do is you're finding the difference between 2000, sorry, I keep putting that one in the wrong place. We're going to start with $2,001, which is the principal, times e to the 0.24 power. And we're going to subtract from that 2,000 times e to the 0.24 power. And that actually turns out to be $1.27. So the approximation is equal to the actual difference. So if you want to write the answer out in context, this is what the answer says. The future value of a 6-year investment of $2,001 will be $1.27 more than the future value of a 6-year investment of $2,000. So I hope these have helped. If you have questions, please let me know. And again, we are having a test soon. Be sure and get this homework caught up.